Back to our next lesson on analyzing a single quantitative variable. In this lesson, we're going to learn how to compare distributions using measures of center and spread. And we'll also explore percentiles and z-scores. These help us to figure out uh, data values that compare data to the rest of a data set. By the end of this lesson, you'll be able to describe the relative position within a distribution and also make meaningful comparisons between different sets of data. So our first sample problems here are on comparing distributions. And when we're comparing distributions, we look at characteristics such as the center, the spread, and the overall variability to identify similarities and differences between groups of data. So here we have a multiple choice question on, it looks like macaws, which are tropical birds, and their lifespans in years. And we have a box and whisker plot for two types or two groups of macaws. We have macaws that are in captivity in the purple, and macaws that were raised or lived in the wild in blue. And so we need to check to see what sort of information we can gather from this. So looking at answer choice A, it says on average, lifespans were longer for macaws in the wild. So A is stating that they were longer in the wild. So we're going to say that the wild is greater than in captivity. Now this is saying on average. On average refers to the mean. When I first saw this, I thought maybe we'll look at the range since we don't have the mean. And that actually was not correct. We don't look at the range in terms of the average. The average means the mean, but it's not supported in a box and whisker plot, so it's not given. So we have to instead generalize with the median as a measure of center. And so if we look at our medians here for the wild and captivity, we can clearly see that the captivity is greater than the wild. So that's not true. We're going to cross out A. A is not correct. For answer choice B, it says the lifespans for all macaws in captivity were longer than those in the wild. Now this one says for every bird in each category. So the lifespan for all the macaws in captivity would include this minimum outlier, and for all of the macaws in the wild would include this maximum outlier. So this is saying the lifespan for B for all macaws in captivity were longer. So we're just going to write what the statements are originally saying just to simplify this a little bit. So it says it's saying that the captivity is longer than the wild. So captivity is greater than those in the wild. For all. So this is the mean. This is for all. And we can clearly see that in captivity, it looks like a lot of them are greater than many of the data points of the macaws in the wild, but not all of them. It looks like here we have in captivity, there's a lower value than those in the wild. So B is not correct either. That is not true for all of them. We could say for most of them, the captivity is the lifespans are greater, but not for all of them, because we do have this outlier here. Okay, so we're going to cross out B. For letter C, it says the lifespans for the macaws in the wild varied more noticeably than those in captivity. So when we're talking about variability, this has to do with the range and the interquartile range. So when we're thinking about variability, we have to assess both of those. Sometimes we only have enough data to check either the range or the interquartile range, but it's a good idea to check both if possible. So in terms of variability, we're going to write the same statement in the less than or greater than statement here. So it says the macaws in the wild, their variability was greater than those in captivity. And this is the variability range in IQR. That's what that inequality statement is referencing. So let's take a look now at the variability for those in the wild. If we look at the range, for the range in the wild, the range looks like it's from about 2, 4, 6, about 77 minus 32. And so we can calculate what the range is, and we get 45 for the range for those birds in the wild. And for the captivity, we're just subtracting the minimum minus the maximum and finding the absolute value. So this is 62 for 66 for our lower value and 84 for our higher value. All I'm doing is I'm subtracting the maximum minus the minimum to find the range. And we get 18. So now we can see that the range is greater for the birds in the wild, for the macaws that are in the wild. So far we're good with variability in terms of range. Let's check the IQR now. The IQR just tells us that we're checking from quartile 1 to quartile 3. So from here to here, and we're essentially finding the range between Q3 and Q1. It's the interquartile range, and that should be a review for you. So if we're doing the IQR of the birds in the wild, write the green there for both of these. For the birds in the wild, that's 62 minus 48. So we're just doing Q3 minus Q1 to get the IQR. And again, this should be review from our last lessons. We get 14, and then the IQR for the birds in captivity, 80 minus 70. It looks like 73-ish. 70. Yeah, it looks like about 73 there. And these are just estimations. So it looks like the birds in the wild, again, have a higher IQR. So the range for the birds in the wild and the IQR for the birds in the wild are both higher than the range and the IQR for the birds in captivity. So C is true, and D obviously is not true. That's none of the above. All right. So that's just sort of the logic of how you can write this out and solve this mathematically. Now you can also just look at these graphs and you could tell that the IQR is greater for the birds in the wild just by looking at it. You can see that the box is longer for the birds in the wild than the box for the birds in captivity. So you didn't necessarily have to actually calculate the IQR or the range, but I just wanted to show you that you can do that for these if you prefer doing this mathematically. This next example is going to ask us to look at the same sorts of ideas, except now we have a histogram. And this is Minneapolis, Minnesota, and Portland, Oregon. It says they have similar latitudes on the map. So that measures how far north and south that someplace is. And these histograms show the daily high temperatures that were recorded in January 2013 in both of the cities. So we have our histogram here. I'm actually going to move this, if I can. I'm going to move these answer choices up here so that we can see the answer choices with our histograms. Make that a little bit easier. Okay, so it says on average, Minneapolis was colder during January. So just looking at the histograms, Minneapolis is in blue and it says that it was colder than in Portland. Now, we don't really know exactly where the mean is. You could calculate the mean if you wanted to with the weighted mean formula that we had discussed from previous lessons, or you could also estimate the mean. And that was where we think of the graph as a physical object that's made of cardboard, and we sort of try to find the balance point or the pivot point where that would be to where it would be balanced if this was something made of cardboard or paper or something that was able to be have weight on both sides. So I'm just going to do a very rough estimate. I'm going to say there's the mean for Minneapolis, and in fact, maybe it's closer to here. And then for Portland, the mean might be somewhere maybe maybe about there. And I'm just doing a very rough estimation because it's not asking us for the average. It's just saying in general. And so I'm just doing a quicker estimation. But we can see that Minneapolis is colder during January. So that's true. Um, it's about -5 for Minneapolis, and it's about maybe 5 or 6 for Portland. Okay, and the next one, on a given day, it was colder in Minneapolis than in Portland. On a given day, that means every day. So there should not be any overlap if this is true. Um, it says it was colder in Minneapolis than in Portland. So it looks like the coldest temperature in Portland, I'm just going to write the coldest temperature was 1 degree. And the coldest temperature in Minneapolis was -20. And the highest temperature in Minneapolis is 7 degrees. And the highest in Portland looks like 13, possibly 13. So remember, we do have a histogram, so we don't know that it's 13 and 7. I'm just generalizing here. So it says on a given day it was colder in Minneapolis. That means that every single day it would be colder in Minneapolis. So from here to here, it looks like we have colder temperatures. But from 1 to 7 degrees in Minneapolis, we also have temperatures ranging from 1 to 7 degrees in Portland. So the key takeaway from this is that there is overlap. So on a given day means every single day it was more or less, in this case, colder in Minneapolis. So this is false. There is an overlap on our graph. The daily high temperatures in January vary more noticeably in Minneapolis. So again, the variation is our range or our IQR. So, or the variation is the range and the IQR. Okay, we can't find the IQR from a histogram alone unless it actually tells us what the IQR is or what quartile 1, quartile 2 is. We cannot find the IQR, but we can find the range. And just like our last problem with the range, I'm just going to write the range of Portland. And it's the highest value minus the lowest value, or lowest minus highest, and you just take the absolute value. The range is going to be a positive value. So that gives us 12. And then the range of Minneapolis is, looks like -20 minus 7. And doing the absolute value here, so we get -27, which is actually positive 27 degrees. So now this says the high temperatures vary more in Minneapolis. So we're saying Minneapolis greater than Portland. And that is a true statement. The range from Minneapolis is greater than that in Portland. And then, of course, it can't be D because we did get an answer C there. Let's look at one more of these with a dot plot. So we've looked at box and whisker plots and histograms. Now let's look at one with a dot plot. This says, before sending track and field athletes to the Olympics, the U.S. holds a qualifying meet. And there's a dot plot that shows us the time in seconds of these 8 sprinters who completed in the women's 100-meter dash at the 2012 Olympic Games. The upper dot plot shows the time for the top 8 sprinters in the U.S. qualifying meet, and then the blue is for the Olympic final times. And says which pieces of information can be gathered from these plots. For A, it says the times in the Olympic final were faster on average than the top 8 U.S. qualifier times. Okay, so we could use our mean rule again for this, or we could actually calculate what the mean is and see if it's true or false. Remember, our mean rule is we try to get a general idea of an estimation of where would the pivot point be if we estimated what the average is. And I'm just going to do a quick estimation first, and then we'll actually do the calculations. And the reason we'll do the calculations is because we actually can do the calculations for this. We're given all of these different data points in order to make these calculations. And I'm just estimating where I think the center is going to be. This is if we had if we treated these dots as weights on a piece of cardboard or something like that, and we're looking for the center, which would be its balancing point. So that's my estimation where the mean would be. But now let's actually calculate it. So the US mean, and we have to look very carefully at where all of these are located, and just to kind of speed things up for this lesson, I'm just going to write them fairly quickly. So 11.06, 11.1 plus 11.1 plus 11.12 plus 11.13 plus 11.15. And then we've got one more, and this is for the green, plus 11.7. Okay, and now we're going to divide, and we get 8 total. So we have 8 sprinters, 8 data points. Now, if we find the US mean, if we continue to add these together, we get 88.79 over 8. And so for the US mean, you get 11.1. So that's our mean for the US. And I think I was fairly close to that. I might have done maybe 11.11 or something where my line was, but that's the mean for the US. And I'm just going to put that in green so we have it green. For the Olympic mean, we're going to do the same thing. We're just going to add up each of these data point values and divide by 8. There's also 8 people racing. So 10.75 plus 10.78 plus 10.81 plus 10.85 plus 10.89 plus 10.94. And if it's a little tough for you to see all of these exactly, I'll zoom in here in just a minute, and then you can do a screenshot if you are wanting to take notes along with this, and see if you're getting these same values also. And then we're going to divide by 8. So here's zoomed in of our data. So if you want to take a screenshot of that, and if that's helpful for you, then go ahead and do that. So all of these, each of these marks on the graph is making the graph go up by 1/100th of a second. All right, so continuing our Olympic average calculation. And again, you don't have to do this. If you're able to estimate, that's great. And I think from our estimation alone, we probably could have gotten an answer. But again, this is just some quick review on how to find the average. Okay, we get 10.88. Now let's take a look at what our question was asking us. Our question said, for on average, for A, it said the Olympic was faster than the US times. So when we're talking about faster, this means that the Olympic times are going to be less than the US times. That's what faster means. Faster equals less in terms of time. So it does look like that's a true statement. The Olympic time's 10.88 on average, and the US average is 11.1. So that is true. Again, just by looking at this, we can estimate the average and we can see that uh, that the Olympic times are less than the US times on average just by looking at where our average is. All right, I think we spent a lot of time on letter A. Let's go to B next. It says all of the times were faster than all of the US qualifier times. All of the Olympic times were faster than all of the US times. Well, it looks like all of these times on the Olympic times were faster. Um, but we have these two outliers in the Olympic final that were about 11 seconds. And then we have one US time that looks like it was faster than those two times that were at about 11 seconds. So we cannot say that all of the Olympic times were faster. So B is not true. Okay. And then finally, the variability. It says the Olympic times vary more noticeably than the US times. And again, we're just going to check our range for this one. There's no way for us to calculate, well, let's see here. We could calculate the IQR for this. Excuse me. We could calculate the IQR. We could list out every single point, but that would take considerably more time. I think the range already provides enough evidence to support our conclusion about if the Olympic times varied more noticeably than the US times. So here, if we just look at our range for the Olympic times, we're going to say for the range for let's start with the US. The range for the US times, it looks like 10.96 was our lowest time. And again, you can estimate with this. You don't have to do the math for this. I'm just showing you that you can calculate mathematically by checking the minimum minus the maximum, finding the absolute value. We get about 0.21 for the range for the US times. The range for the Olympic times, we're also doing minimum minus the maximum. And that looks like the minimum is 10.75 and the maximum is 11.01. Let me see, yeah, 11.01. And we're finding the absolute value of this. So if you ever get a negative with the range, just remember it's the positive absolute value. Okay, so it says the Olympic times varied more noticeably. This was the Olympic times variation, or the range was 0.26. And yes, it varied more than the US times of 0.21. Okay. And this one it looks like we could probably, you might be able to do this without writing out the range, but these are very close numbers. So you might have to do the calculations for those sometimes. All right. So I think that this first section is very conceptual. It can be a little bit challenging, I think, to write down notes for this section also, because it's a very conceptual type of problem set. We're going to go on to calculating percentiles next. When we calculate percentiles, there are two different formulas that we can use. to calculate percentiles. This first example asks us to find the interval that has the 25th percentile for the data. So when it's asking us to find the interval, we're going to use the formula called the percentile position formula. And the percentile position formula is when you're given a percentile and we want to find the value or the interval. You want to find, I'm just going to say want to find, we'll say want to find the interval. All right. So to calculate the 25th percentile, and sometimes percentile is written like that. The percentile position formula, let me write the formula first above here. Percentile position formula is just the percent as a decimal times n. Let me write it like this. Percent times n, and then times 100. Because we have to multiply our decimal times 100 to change the percent. Anyway, let's see here. So we're going to write 25%, 0.25 times n. There's 192 data points in this. And that gives us 48. And I'm actually going to change. We don't put times 100. We're just going to say the percent as a decimal. And that should be, I think, intuitive for us now being in stats. You're right, percents as decimals. So it's just the decimal percent times the total number. And that's 48. So now we're going to find the interval where 48 lies. So 48, everything to the left of where the 48th speaker is located is within the 25th percentile. So it looks like from 0 to 1, there are 60 speakers. So at 48 would be about there. So our 25th percentile is going to be from 0 to 1 hour. Look at that on our x-axis of our graph. Okay. So again, we don't times by 100 for this percentile position formula. It's just the percent times n. For our next example, we're going to use the percentile rank formula. When we're given a value and we need to find the percentile, we use the percentile rank formula. And the percentile rank formula is the number that we are at or below, the number that is identified. In this case, it's saying find the percentile for a hydrangea with a 5.2 inch diameter. So that's the number at or below X over our total number of data points. So this is about this person ordering flowers to decorate for a wedding, hydrangeas. And the stem plot tells us these different diameters of the 35 hydrangeas that showed up for the wedding. And we want to find the closest estimate to the percentile for a hydrangea with a 5.2 inch diameter. So first, we're going to figure out how many values are at or below 5.2. So we're going to count the number at or below 5.2. So that's what it's asking us to find a percentile for 5.2. So we're going to read our stem and leaf plot. So we've got 3.9 for the first one, 4.0, 4.0, 4.3, 4.6, 4.6, 4.6, 4.6. Let's make sure we have those correct. 1, 2, 3, 4. 1, 2, 3, 4, 4.6s, 4.8, 5.0, 5.1, 5.1, and at or below 5.2. So we are going to include 5.2 because it's at 5.2. Now we're going to count how many of these data values exist. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 values altogether. So that's our numerator for this. We have 13 on our numerator. Now the second step, we're going to convert to a percentile. Okay, again, we're going to use the percentile rank formula to do that. So we're just going to say 13 is our numerator over n. And there's 35 total values in this data set. N is equal to 35. And so we get 13 over 35, which is 0.371, or approximately 37.1%. Okay, and that is our, back up here, and that's our percentile. So the closest estimate is the 37th percentile for this. Okay, so again, the percentile position formula is when we're given the percentile and we want to know the position or the number that's associated with the percentile or the interval. And the percentile rank formula is when we're given a value and we need to find what the percentile is, like this second example here. Okay, let's look at one more of these. This one tells us the 60th percentile. It wants us to find the interval that contains the 60th percentile for this data. And this histogram summarizes the number of tropical storms per year in the US for 30 years. Okay, so we're gonna find the percentile position. We're given the percentile, we want to find the position. Percentile position formula. Okay, and that one was percent times n. So we have the percent is 60th percentile, or 0.60, times n, which is, it looks like n is equal to 30. Done this for 30 years. And so that equals 18. So now we're going to look for the 18th value. So from 0 to 25 is 1 year. From 25 to 50, you write this out, from 0 to 25 is 1. From 25 to 50 is 7. And we're trying to go up to 18 and figure out which interval contains 18. So this is 7. From 50 to 75 is 5. From 75 to 100 is 4. From 100 to 125 is 3. So let's add this up so far and see if we get to 18. So if we add these just on the right side, we have 8. 1 plus 7 is 8, plus 5 is 13, plus 4 is 17. So this would be the 17th value from 75 to 100. And looks like the 18th value is going to be in the interval of 100 to 125. All right. The last section today, we're going to cover calculating z-scores. And we're just going to look at the some of the basics of z-scores. And we are going to revisit z-scores and z-tables in some later lessons. But for now, we're just going to sort of go over the basics of z-scores. Z-scores tell us how far a data value is from the mean in terms of standard deviations. So this allows us to compare different values from different data sets. We also call z-scores a standard score. It tells us how many standard deviations that a data value is above or below the mean. So z-scores, they measure the distance in standard deviation. And this is our formula for a z-score. To find the z-score, we take the data point minus the mean and divide by the standard deviation. And z-scores are very helpful because in the real world, most data sets are approximately normal data distributions, meaning they form this bell-shaped curve uh, where most of the values are clustered near the mean. So we have a higher curve here in the center. And we can make generalized assumptions based on the probability of data falling within standard or a certain amount of standard deviations from the mean. Okay. When we're looking at a z-score, z equals 0. When we get a z-score of 0, it means that it's exactly at the mean. When we have a z-score of greater than 0, if it's anything that's more than 0, even if it's 0.01, we can say that it's above the mean. And if it's less than 0, then it's below the mean. So this would be a z-score of 2. This would be a z-score of 3, so on. So that's how you read that on the bell curve. Z-scores, they help us to compare values from different distributions by placing them on the same standardized scale. So if we can convert data values into z-scores, we can use the standard normal distribution, and that can help us to determine percentiles, probabilities, and areas under the curve. And so we're able to find those things from calculating the z-score. But let's just look at some z-score calculations. These should go fairly quickly. We're given, for example, one, the mean and the standard deviation. And it says that this person, they scored 64 on their exam. And so this is the data point that they give us. This is about grades on a math midterm. And it's saying that they're roughly symmetric, so we're using a bell-shaped distribution for this. And it just wants us to find the z-score. So z is equal to our data point minus the mean divided by the standard deviation. So we have 64 minus 76 divided by 4.5. So it gets -8 over 4.5. Sure, I did that correctly here. 64 minus 76, 4.5. Yeah, it gives us about -2.667. And that's all we need to find for these. Now, in later lessons, we're going to look at how we are able to interpret this number in terms of finding percentages and percentiles. But let's just take a look at our 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 normal distribution now and see where that would put us. So negative 2.67 would be somewhere about here. So when we measure z-scores, we are looking at usually everything to the left of this. But anyway, that's what our z-score would be, or that's where it would be located on the distribution. Okay, let's look at a couple more of these, and then we'll get into some more details on z-scores when we talk more about normal distributions. Okay, one more. We're going to say this is x minus the average over standard deviation. And this is 65 minus 69 over 3.5. Again, this is grades on a test for a data set of grades on a test. We're given the mean standard deviation and this one person's score, which is our data value x. So x is 65. And then we just solve for what z is, and we get negative 4 over 3.5. And that equals negative 1.1428 for our z-score. And it wants us to round to 2 decimal places for this, so negative 1.14 is our final answer for this. Okay, so when you get the z-score, there's something called a z-score table. And we have two different tables, one for negative z-scores and one for positive z-scores. But these tell us the percentages for standard deviations by looking at the z-score table. So we would go to our table, in this case, negative 1.14, and we'd look for where that's located. Negative 1.14. So we're going to find negative 1.1 first, which is right here. And then these columns are the hundredths column. So negative 1.1, and then we're going to find where it lines up with the 4, which is right here. And so this is our percentage for a z-score of negative 1.14. And the z-score of negative 1.14, this means that 12.714% of our data is less than, or it's below this value. So this value is 1.14 standard deviations below the mean. So our z-score of negative 1.14 would be about here. That's 1.14 standard deviations below the mean. And that means that roughly 12.714% of our data is below this value. All right, so that is everything on comparing distributions, uh, percentiles, and z-scores. And again, we're going to revisit z-scores in the future, but all of these tell us or help us to compare values and understand where they fall within distributions.